What if everything you see in the night sky, the stars, the galaxies, the swirling nebulas, were just tiny dots dangling from an invisible, unimaginably vast skeleton? Picture this, an intricate network of threads woven across billions of light years, connecting every galaxy like beads on a cosmic string. This isn't science fiction. It's real, and it's called the cosmic web, the hidden architecture of the universe itself. For centuries, we looked up and saw only isolated islands of light scattered across the darkness. But now, thanks to groundbreaking telescopes and supercomputer simulations, we're uncovering the truth. The universe isn't just a random scattering of galaxies, it's a carefully structured masterpiece, held together by filaments of dark matter and gas so thin, so faint, they're nearly invisible. These filaments form the backbone of existence, shaping everything from the tiniest star clusters to the largest superclusters. And here's the wild part: without this web, galaxies like our own Milky Way wouldn't exist. Think of it like this: if the universe were a living organism, the cosmic web would be its nervous system, an invisible network pulsing with energy, guiding the growth of galaxies and dictating the fate of everything we know. It's the ultimate cosmic blueprint, and we're only just beginning to decode its secrets. So how do you map something so vast, so elusive? What happens when we finally see the universe not as a collection of isolated points, but as a single, interconnected structure? Strap in, because we're about to take a journey into the deepest reaches of space, where the fabric of reality itself reveals its hidden design. Let's zoom in on this cosmic skeleton for a moment. The cosmic web isn't just a poetic metaphor, it's the literal framework of existence. Imagine dark matter, that mysterious, invisible substance making up most of the universe's mass, stretching across space in vast, thread-like filaments. These strands are the universe's hidden scaffolding, thinner than spider silk but strong enough to shape galaxies over billions of years. Where these filaments intersect, galaxies gather like cities at the crossroads of an ancient trade route, drawn together by gravity's relentless pull. But here's where it gets even wilder. The spaces between these threads aren't empty, they're cosmic voids, unimaginably vast deserts where galaxies are few and far between. Picture the web as a sponge. The dense filaments are the walls, while the voids are the holes, stretching hundreds of millions of light years across. This structure isn't random. It's a fossil record of the universe's infancy, echoing patterns first imprinted by tiny quantum fluctuations moments after the Big Bang. Over eons, gravity amplified those ripples, sculpting them into the colossal network we see today. And the galaxies, they're not just passive passengers. They slide along these filaments like beads on a string, pulled toward the densest nodes where clusters collide and merge in slow-motion cosmic dances. Without this web, galaxies would drift apart like unmoored ships, scattered and isolated. Instead, they're bound together in a grand, dynamic tapestry, one we're only now learning to trace. Scientists use supercomputers to simulate its growth, mapping how dark matter's invisible tendrils guide the birth of galaxies, stars, and even planets like ours. It's the universe's ultimate connect-the-dots puzzle, and every new observation brings us closer to seeing the full picture. Dark matter is the universe's greatest mystery and its most powerful architect. While it doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes, its gravitational pull is the force weaving the cosmic web into existence. Think of it like the wind. You can't see it, but you feel its effects in the sway of trees or the rush of a storm. Dark matter works the same way. Its gravity tugs on galaxies, guiding them into filaments and nodes, shaping the largest structures in the cosmos over billions of years. Without it, the universe would be a formless sea of scattered stars, never able to clump into the galaxies and clusters we see today. But how do we know dark matter is there if we can't see it? The clues are everywhere. When astronomers measure how galaxies rotate, they notice something strange. The stars at the edges move just as fast as those near the center, defying the laws of gravity as we understand them. The only explanation, an invisible halo of dark matter wrapping around each galaxy like an unseen hand holding it together. Then there's gravitational lensing, light from distant galaxies bending around massive objects in ways that only make sense if there's far more matter present than what's visible. These cosmic fingerprints reveal dark matter's presence, mapping its hidden contours across the universe. The most astonishing part, dark matter doesn't just hold galaxies in place, it dictates where they form in the first place. In the early universe, slight density variations in dark matter acted like cosmic seeds. Gravity amplified these tiny ripples, pulling gas and dust into the densest regions where stars and galaxies eventually ignited. The filaments of the cosmic web trace these ancient pathways, with galaxies strung along them like lights on a holiday garland. Even now, dark matter's gravitational currents guide the motion of galaxies, pulling them toward colossal intersections where clusters collide in slow, spectacular mergers. Yet for all its influence, dark matter remains frustratingly elusive. Scientists have hunted for direct evidence for decades, using detectors buried deep underground to shield them from cosmic noise. So far, no definitive signal has been found. Some theories suggest dark matter could be made of exotic particles, entirely unlike anything in our familiar world. Others propose modifications to gravity itself, though these ideas struggle to explain all the observations. What's clear is that solving this puzzle won't just reveal the secrets of the cosmic web, it could rewrite our understanding of physics. Until then, dark matter remains the universe's silent sculptor, shaping everything we see while staying forever just out of sight. Galaxies don't just drift randomly through space, they gather where the cosmic web's filaments collide, clustering like bustling metropolises at the intersections of invisible cosmic highways. These intersections, where multiple dark matter threads knot together, become the universe's most crowded neighborhoods. Picture a colossal freeway interchange where highways merge and traffic slows, creating hubs of activity. In the same way, gravity traps gas, dust, and galaxies at these crossroads, compressing them into dense, glowing knots we call galaxy clusters. Some of these clusters contain thousands of galaxies, each with billions of stars, all bound together in a gravitational dance that's lasted billions of years. But why do galaxies prefer these intersections? It all comes down to gravity's relentless pull. As dark matter filaments weave across the universe, they funnel gas and dust toward their intersections, like rivers merging into a vast delta. The deeper the gravitational well at these nodes, the more material gets sucked in. Over time, this accumulating matter ignites stars and sparks galaxies, turning sparse intersections into dazzling cosmic metropolises. The largest clusters, like the Virgo cluster near our Milky Way, become anchors in the web, pulling in smaller galaxies and growing even more massive. These hubs aren't static, though. Galaxies within them ricochet and merge, triggering bursts of star formation and sometimes violent collisions that reshape entire regions of space. Here's the mind-blowing part: the way galaxies cluster isn't random at all. Just as cities on Earth form near rivers or trade routes, galaxies congregate where the cosmic web's filaments converge. The voids between these intersections, they're like the universe's deserts, vast, empty expanses where galaxies are rare. This isn't a coincidence. The web's structure determines where galaxies can thrive. Without these dense nodes, matter would spread too thin, and galaxies might never form. Instead, the web acts as a cosmic blueprint, ensuring that matter collects in just the right places for galaxies to blossom. And the Milky Way, we're part of this grand design too. Our galaxy sits along a filament, drifting slowly toward the immense gravitational pull of the Virgo cluster, like a car coasting downhill. In billions of years, we'll merge with other galaxies in our local group, eventually becoming part of an even larger cluster. This slow-motion migration is how the cosmic web shapes the fate of galaxies, guiding them, merging them, and constantly rewriting the map of the universe. By studying these clusters, astronomers aren't just mapping where galaxies are now. They're tracing the invisible threads that have dictated their journey since the dawn of time. Between the dense filaments and bustling galaxy clusters of the cosmic web lie regions so empty, so vast, they defy comprehension. Cosmic voids. These are the universe's true deserts, stretching hundreds of millions of light years across with barely a single galaxy in sight. If the cosmic web is a sprawling metropolis, these voids are the silent, empty stretches between cities, places where matter didn't just thin out, but nearly vanished altogether. Why are these voids so empty? The answer lies in the universe's earliest moments. After the Big Bang, tiny quantum fluctuations created slight variations in density. Some regions had a bit more matter, others a bit less. Over billions of years, gravity amplified these differences, pulling matter into the denser regions to form filaments and clusters while leaving the sparser zones behind. The voids didn't lose matter, they never had much to begin with. Like water draining from a bathtub, gas and dark matter flowed toward the filaments, leaving these regions as cosmic afterthoughts, ghostly expanses where galaxies rarely form. But empty doesn't mean completely barren. Even in the deepest voids, a few rogue galaxies might drift, isolated like lone travelers in an endless desert. These galaxies are often oddballs, small, faint, and strangely quiet, having missed out on the collisions and gas flows that fuel star formation in denser regions. Some may have been flung into the void by gravitational tugs from nearby clusters, doomed to wander the emptiness forever. The scale of these voids is staggering. The largest, like the Boötes void, span over 300 million light-years, so vast that if our Milky Way sat at the center, we wouldn't have seen another galaxy until the 1960s, when telescopes finally became powerful enough to peer beyond our local cluster. Yet despite their emptiness, voids play a crucial role in the cosmic web structure. They're not passive holes, their sheer size shapes how filaments curve and stretch, acting like invisible walls that push matter into ever more intricate patterns. What's even more fascinating is how these voids evolve. As the universe expands, the gaps between filaments grow wider, stretching the voids larger over time. Some cosmologists call them negative galaxies, regions where the absence of matter reveals just as much about the universe's structure as the presence of it. By studying these empty spaces, scientists can trace the inverse blueprint of the cosmic web, mapping where matter isn't to better understand where it is. So while voids might seem like cosmic dead zones, they're anything but. They're the counterbalance to the universe's crowded hubs, the silent partners in the grand dance of structure formation. Without them, the cosmic web wouldn't be a web at all, just a formless, homogeneous haze. Their emptiness, as much as the filament's density, defines the universe we live in. To uncover the secrets of the cosmic web, scientists don't just peer through telescopes, they build entire universes inside supercomputers. These aren't simple animations or artistic renderings. They're precision-engineered simulations where billions of particles of dark matter and gas obey the laws of physics, evolving over cosmic timescales to reveal how the universe's largest structures emerge. One of the most ambitious of these virtual cosmos projects was the Millennium Simulation, run by astrophysicists in Germany in 2005. Here's how it worked. Programmers fed the supercomputer a starting recipe, a digital snapshot of the early universe, just 300,000 years after the Big Bang, based on real data from cosmic microwave background observations. Then they let physics take over. Over months of calculation, the simulation tracked 20 billion particles, each representing a clump of dark matter, as gravity pulled them into filaments, nodes, and voids. Watching the results was like hitting fast forward on 13 billion years of cosmic history. The simulation revealed something astonishing. the faint ripples in the early universe's density, imprinted by quantum fluctuations, grew into the vast filamentary structures we see today. The cosmic web didn't form randomly. It unfolded like a predetermined blueprint, with galaxies naturally clustering where dark matter filaments crossed. But the Millennium Simulation was only the beginning. Today, projects like LSST and Eagle push the boundaries even further, incorporating not just dark matter but ordinary gas, stars, black holes, and magnetic fields. These simulations are so detailed they can predict where and when galaxies should form, how they evolve, and even what kinds of stars they'll contain. When astronomers compare these virtual universes to real telescope surveys, the match is uncanny, like holding up a mirror to nature itself. The real magic happens when simulations reveal something telescopes can't see. For example, they've shown how cosmic voids aren't perfectly empty but contain faint, wispy filaments too thin for current instruments to detect. They've also exposed the violent past of galaxy clusters, where collisions between dark matter halos send shockwaves through intergalactic gas, heating it to millions of degrees. Without simulations, we'd have no way to piece together these invisible chapters of cosmic history. Yet even the most advanced simulations have limits. The universe is simply too big, too complex to model down to every atom. Supercomputers must make trade-off, simplifying some physics to save processing power, or zooming in on small patches of space to capture fine details. That's why each new generation of supercomputers, like those powered by exascale processing, aims to narrow the gap between simulation and reality. Imagine a virtual universe so precise it could predict the exact arrangement of galaxies in a patch of sky, or trace the path of a single hydrogen atom from the Big Bang to the present. We're not there yet, but with each leap in computing, we get closer to cracking the cosmic web's deepest mysteries. What's truly groundbreaking is how these simulations don't just replicate what we know, they predict what we don't. When the Milky Way's faint satellite galaxies didn't match early dark matter models, simulations helped tweak the recipe, revealing that small galaxies form differently than large ones. When telescopes spotted galaxies in the early universe that seemed too mature to exist so soon after the Big Bang, simulations showed how intense bursts of star formation could accelerate their growth. It's a constant dialogue between digital universes and real observations, each refining the other. The ultimate goal, a simulation so accurate it becomes a time machine, letting us rewind the universe's tape to witness its birth or fast forward to see its distant fate. Until then, every line of code, every calculation, brings us one step closer to answering the biggest question of all. How did a near-uniform soup of particles after the Big Bang transform into the dazzling, structured cosmos we call home? The cosmic web's blueprint is written in the language of dark matter and gravity, and with supercomputers as our translators, we're finally learning to read it. The story of the cosmic web begins not in the vast emptiness of space, but in the unimaginable heat and density of the Big Bang itself. Picture the universe in its first fleeting moments, a seething, glowing soup of particles so hot that matter and energy were indistinguishable. In that primordial chaos, something remarkable happened. Tiny quantum fluctuations, no larger than a billionth of a meter, rippled through the infant cosmos. These microscopic wrinkles in space-time might seem insignificant, but they held the seeds of everything we see today: the galaxies, the filaments, even the voids. Here's how it worked. As the universe expanded and cooled, gravity went to work on those tiny density variations. Imagine blowing up a balloon with faint ink stains on its surface. As the balloon stretches, those stains don't just grow, they warp, their edges pulling inward, their centers growing denser. That's precisely what happened to the early universe's fluctuations. Regions with slightly more matter exerted stronger gravitational pulls, drawing in nearby gas and dark matter like cosmic magnets. Over millions of years, these overdense patches grew into dense knots, while underdense regions stretched into ever-expanding voids. But gravity didn't act alone. Dark matter, the universe's invisible scaffold, played the starring role. Unlike ordinary matter, which can collide, heat up, or radiate light, dark matter interacts only through gravity. This meant it could clump together undisturbed, forming vast tendrils that stretched across the expanding universe like an invisible skeleton. Ordinary matter, the stuff of stars and galaxies, simply flowed into these pre-existing dark matter channels, like water filling the grooves of a riverbed. By the time the first stars ignited, the cosmic web's blueprint was already in place, its filamentary structure imprinted in the distribution of galaxies we see today. The echoes of this process are still visible in the cosmic microwave background, the faint afterglow of the Big Bang. Satellite missions like Planck have mapped its subtle temperature variations, revealing a pattern that matches the web's modern structure. Those tiny hot and cold spots, they're the quantum fluctuations of the early universe frozen in time, their gravitational consequences playing out over billions of years. It's as if we've found the universe's baby photos and they contain the first scribbles of the cosmic web's design. What's truly staggering is the scale of transformation. Those initial ripples, smaller than an atom, ballooned into structures hundreds of millions of light years across. The densest nodes in today's web, colossal galaxy clusters like the Coma cluster, trace their ancestry directly back to microscopic hotspots in the infant cosmos. Meanwhile, the voids we see today are the descendants of those early underdense regions, stretched to incomprehensible sizes by cosmic expansion. The universe didn't just grow, it evolved, its structure becoming ever more intricate as gravity wove matter into the grand tapestry we now observe. This process wasn't instant. It took billions of years for gravity to sculpt the cosmic web into its current form. Early on, the universe was too hot and dense for galaxies to form. Only after 300,000 years, when atoms finally coalesced from the cooling plasma, could matter begin clumping in earnest. The first stars ignited around 100 million years later, their ultraviolet radiation helping to strip electrons from surrounding gas, a process called reionization that further shaped how matter flowed into filaments. By 1 billion years after the Big Bang, the web's basic framework was set, with young galaxies already aligning along faint protrusions of dark matter. Today, we're witnessing the aftermath of this epic construction project. The Milky Way and its neighbors aren't floating in isolation, they're embedded within a local filament, part of the Laniakea supercluster, which itself is just one strand in the cosmic web's unimaginably vast architecture. Every galaxy, every cluster, every void is a direct consequence of those quantum ripples from the dawn of time, amplified by gravity into the largest structures nature has ever produced. The web isn't static either. Even now, galaxies slide along filaments toward waiting nodes, drawn together by the same gravitational forces that have shaped the universe since its birth. Understanding this connection between the Big Bang's quantum seeds and today's cosmic web doesn't just satisfy curiosity, it helps solve practical mysteries. For instance, by studying how clusters form at filament intersections, cosmologists can measure the universe's expansion rate and composition. The web's structure holds clues to dark energy's nature, the fate of the cosmos, and even potential cracks in our current physics theories. Every time we map a new section of filaments or measure a void's growth, we're reading a chapter in the universe's autobiography, one that began with a whisper of quantum noise and unfolded into the magnificent cosmic cityscape we call home. Peering into the vast darkness of space and mapping something as elusive as the cosmic web might seem impossible, but astronomers have developed ingenious ways to trace its invisible threads. One of the most powerful tools in their arsenal is the redshift survey. Here's how it works. As the universe expands, light from distant galaxies stretches, shifting toward the red end of the spectrum. By measuring this redshift, scientists can calculate not just how far away a galaxy is, but how fast it's moving. Projects like the Sloan Digital Sky Survey have taken this idea to staggering scales, mapping millions of galaxies across a quarter of the visible sky. When you plot those galaxies in 3 dimensions, something extraordinary emerges. They don't scatter randomly. Instead, they align along vast, interconnected filaments, tracing the cosmic web's hidden architecture in dazzling detail. But redshift surveys only show us where the galaxies are. What about the dark matter filaments connecting them? That's where gravitational lensing comes in. Imagine space as a rubber sheet and massive objects like galaxy clusters as weights pressing down on it. When light from a distant galaxy passes near one of these clusters, the sheet bends, and so does the light. By studying these distorted images, astronomers can map the invisible mass warping space, revealing dark matter's ghostly tendrils. The Hubble Space Telescope has captured some of the most dramatic examples, where entire galaxies appear stretched into faint arcs, betraying the presence of colossal filaments we'd otherwise never see. The real breakthrough, though, comes from combining these techniques. Take the Dark Energy Survey, which used both galaxy positions and gravitational lensing to create one of the most precise maps of the cosmic web ever made. By cross-referencing redshift data with lensing distortions, scientists could reconstruct not just where dark matter lurks, but how it's distributed, showing filaments as fine as spider silk stretching between galaxies. Some of these threads are so tenuous they contain just 1 atom per cubic meter, yet they span millions of light years, binding galaxies together in a cosmic embrace. Technology has turbocharged this mapping process. Modern telescopes like the James Webb Space Telescope peer deeper into the early universe than ever before, catching galaxies as they first aligned along nascent filaments. Meanwhile, instruments like the Dark Energy Spectroscopic Instrument can measure redshifts for 50,000 galaxies in a single night, a task that once took years. Supercomputers then stitch this data into 3-dimensional models, simulating how dark matter's gravity sculpted the web over billions of years. The result: a map so precise it predicts where undiscovered galaxies should be, and astronomers often find them exactly where the models suggest. But the most astonishing revelations come from peeling back layers of time. When telescopes like Webb observe extremely distant galaxies, they're seeing the universe as it was just 1 billion years after the Big Bang, and even then, the Webb's infant framework is visible. Protofilaments already channel gas into dense knots, sparking furious bursts of star formation. These observations confirm a mind-bending truth: the cosmic web didn't emerge gradually. Its foundations were laid shockingly early, with dark matter's gravitational blueprint guiding galaxy growth from the universe's first chapters. Yet for all our progress, huge gaps remain. Current telescopes can't detect the faintest filaments, and mapping the web in full would require surveying billions more galaxies. That's where upcoming missions like the Euclid Space Telescope and the Vera C. Rubin Observatory come in. With cameras capable of capturing the entire visible sky every few nights, they'll generate petabytes of data, revealing the web's structure with unprecedented clarity. Some scientists even dream of detecting dark matter directly, perhaps through its subtle gravitational ripples, to see the cosmic web not just in outline but in vivid relief. What makes this quest so thrilling is how it transforms our cosmic perspective. Every new map shows us not just where we are in space, but how we fit into the universe's grand design. The Milky Way isn't floating in isolation, it's part of a local filament, drifting toward the Virgo cluster, one thread in a tapestry woven across billions of light years. And with each technological leap, we pull back another layer of the veil, glimpsing the universe not as a scatter of stars, but as the intricately connected masterpiece it truly is. The Sloan Digital Sky Survey didn't just observe the universe, it transformed our understanding of cosmic structure. When this ambitious project began in the late 1990s, astronomers knew galaxies clustered together, but no one had mapped their positions on a massive enough scale to see the bigger picture. The solution was revolutionary: a dedicated 2.5-meter telescope at Apache Point Observatory, New Mexico, equipped with a camera so sensitive it could capture millions of galaxies in stunning detail. Night after night, the telescope's robotic system scanned the sky, recording the brightness, color, and position of every object in its field of view. But the real breakthrough came when researchers paired these images with spectra measurements of light split into its component wavelengths. By analyzing the redshift of hundreds of thousands of galaxies, the survey didn't just show where they were, it revealed how they moved, exposing the gravitational pull of the cosmic web's hidden filaments. The results were staggering. For the first time, scientists could visualize the universe's skeleton in 3 dimensions. Early data releases showed galaxies arranged in vast, interconnected walls, structures like the Sloan Great Wall, stretching nearly 1.4 billion light-years across, one of the largest known formations in existence. These weren't random clusters, they traced the dense ridges of dark matter filaments, with voids yawning between them like cosmic canyons. The survey's precision was unprecedented. By measuring redshifts for over 2 million galaxies, SDSS revealed finer threads in the web-delicate tendrils connecting smaller galaxy groups, and even lone galaxies strung along filaments like solitary lights on a country road. But SDSS did more than map structure. It illuminated how the cosmic web evolves. By comparing nearby galaxies to those billions of light-years away, astronomers saw how filaments grew denser over time, with galaxies migrating toward nodes in a slow-motion cosmic dance. The survey also exposed quirks in galaxy formation. Spiral galaxies like our Milky Way tended to avoid the densest cluster cores, preferring filament edges, while elliptical galaxies dominated crowded intersections, evidence that a galaxy's environment, shaped by the web, dictates its fate. Perhaps the survey's most profound contribution was democratizing cosmic exploration. Unlike earlier projects that hoarded data, SDSS made its findings public, allowing anyone from high school students to Nobel laureates to mine its treasure trove of maps and spectra. This open approach sparked discoveries no one anticipated, from dwarf galaxies hiding in nearby filaments to rare quasars illuminating the web's most distant reaches. Today, SDSS continues with advanced instruments like BOSS and eBOSS, probing deeper into dark energy's role in sculpting the web. What began as a sky survey became something far greater, a mirror held up to the universe's grand design, showing us we're not just observers of the cosmic web, but part of its ever-unfolding story. The next chapter in our cosmic cartography is about to unfold, with missions designed to peel back the universe's hidden layers like never before. Leading this charge is the Euclid Space Telescope, a European Space Agency project poised to launch a revolution in how we see the invisible scaffolding of the cosmos. Unlike conventional telescopes that focus on visible light, Euclid's infrared eyes and precision optics will chart the shapes and positions of over 1 billion galaxies across 10 billion light-years, mapping the cosmic web's structure with razor-sharp clarity. But here's the game changer: Euclid won't just snap pretty pictures. It'll measure subtle distortions in galaxy shapes caused by gravitational lensing, revealing the exact distribution of dark matter filaments with unprecedented detail. Imagine tracing every backroad in a continent-spanning highway system. That's the level of resolution Euclid promises, exposing faint tendrils too wispy for current telescopes to detect. Then there's the Vera C, Rubin Observatory's legacy survey of space and time, or LSST, set to redefine sky surveys. Perched atop a Chilean mountain, its 3.2 billion pixel camera will scan the entire southern sky every 3 nights for a decade, creating a time-lapse movie of the universe. This relentless observation will catch galaxies drifting along filaments in real time, tracking their motions with such precision that scientists can reconstruct the gravitational forces tugging at them, essentially weighing the cosmic web's hidden dark matter threads. LSST true power lies in volume. It'll catalog 40 billion galaxies, spotting dwarf galaxies nestled in faint filaments that older surveys missed. These cosmic stragglers hold clues to how the web's finest threads influence galaxy formation, like how backwater towns reveal a nation's cultural fabric. What sets these missions apart isn't just technology, it's strategy. Euclid and LSST complement each other like detectives solving the same case from different angles. Euclid's deep, narrow-field infrared vision peers into the early universe, catching filaments as they first assembled. Meanwhile, LSST wide-field optical surveys provide context, showing how those ancient structures evolved into today's web. Together, they'll test bold theories like whether dark matter's cold nature moving slowly in the early universe truly explains filament formation, or if exotic physics like warm dark matter played a role. There's even potential to spot primordial black holes lurking in filaments, predicted by some models as dark matter candidates. The data deluge from these projects will be staggering. Euclid's 10-year mission will generate petabytes equivalent to streaming high-def video for 200,000 years, while LSST nightly data dumps could fill 1,000 laptops daily. Processing this requires AI capable of spotting cosmic patterns humans might miss, like filaments warping space in unexpected ways. Already, machine learning tools are being trained on simulated universes to recognize these subtle signatures, preparing for the flood of real observations. But the biggest surprises may come from beyond the web's architecture. Both missions aim to measure dark energy's influence on how filaments stretch over time, probing why the universe's expansion is accelerating. Some theories suggest dark energy's repulsive force prevents matter from fully collapsing into filaments, leaving the web perpetually under construction. Others speculate that the voids between filaments are expanding faster than the web itself, a cosmic tug-of-war that could determine the universe's ultimate fate. Looking further ahead, projects like NAS and Nancy Grace Roman Space Telescope will join this cartographic crusade in the 2030s, adding even sharper infrared vision. Combined with next-generation radio arrays mapping hydrogen gas along filaments, we're nearing an era where the cosmic web isn't just sketched in broad strokes but rendered in photorealistic detail. These missions won't just fill in gaps, they'll rewrite our understanding of gravity, particle physics, and the universe's birth pangs. The invisible skeleton of existence is finally stepping into the light, and what we uncover may redefine our place within it. The cosmic web doesn't just arrange galaxies, it feeds them. Those faint, sprawling filaments act like cosmic pipelines, channeling vast rivers of gas directly into galaxies where it ignites into new stars. This isn't a gentle trickle, it's a high-pressure delivery system, shuttling fuel across millions of light years to keep galaxies alive. Think of a tree's roots drawing water from the soil, except here, the roots are invisible dark matter threads, and the water is hydrogen gas, the raw material for star formation. Without this intricate network replenishing their fuel supply, galaxies would burn through their gas reserves in a cosmic blink, fading into darkness long ago. Here's how it works. As gravity pulls gas into the cosmic web's filaments, it doesn't flow smoothly. The gas crashes into itself, shock heating to millions of degrees and glowing faintly in X-rays. These collisions create a turbulent, high-speed highway where gas rushes toward filament intersections, the same nodes where galaxy clusters form. But not all the gas makes it to the end of the line. Along the way, some cools and condenses, dripping onto galaxies like dew on a spiderweb. The Milky Way is no exception. Our galaxy sits nestled within a filament of the Laniakea supercluster, and we're still receiving deliveries. Astronomers have spotted clouds of hydrogen gas streaming toward us along these invisible pathways, fresh fuel for future star birth. Some of this gas is pristine, untouched since the Big Bang, while other streams are laced with heavier elements, recycled material from ancient supernova, ejected long ago and now returning home. This constant inflow solves a cosmic mystery: how galaxies like ours keep forming stars for billions of years without running out of fuel. The answer was right above us all along, hidden in the web's delicate threads. But the web's influence doesn't stop at gas delivery. It shapes galaxies in more surprising ways. When two filaments intersect, the resulting flood of gas can trigger starbursts, where galaxies suddenly blaze with newborn stars at rates hundreds of times higher than normal. We see this today in galaxies like the Antennae, where colliding gas streams have ignited fireworks of star formation. Simulations show these events were even more extreme in the early universe, when the web's filaments were denser and gas flowed more freely. Some of today's giant elliptical galaxies may owe their size to ancient starbursts sparked by cosmic intersections. The flip side, galaxies cut off from the web face a slow starvation. In the voids between filaments, isolated galaxies scavenge what little gas they can find, often growing stingy with star formation. These red and dead galaxies, heavy with aging stars but devoid of new ones, are like cosmic deserts, places where the web's life-giving flow never reaches. Their fate hints at what could have happened to all galaxies without the web's constant nourishment. Yet even starvation isn't the end of the story. Recently, astronomers discovered some void galaxies defying expectations, somehow reigniting star formation after eons of quiet. The culprit, the web's faintest, most far-flung filaments, too tenuous to see directly but still capable of funneling trace amounts of gas into the void. It's a reminder that the cosmic web works in subtle ways, its influence reaching even the universe's loneliest corners. The most astonishing twist comes when we look back in time. Telescopes like JWST have spotted young galaxies in the early universe aligned along filaments, already feeding from gas streams just a billion years after the Big Bang. These infant galaxies shouldn't have been able to grow so fast under normal conditions, but the web gave them a head start, concentrating gas exactly where they needed it. In a very real sense, the Milky Way's existence today traces back to these ancient rivers of gas, flowing along a blueprint written in dark matter. The cosmic web isn't just the universe's skeleton, it's its circulatory system, keeping galaxies alive across the eons. Dark energy is the enigmatic force stretching the universe apart at an ever-increasing rate, and its fingerprints are all over the cosmic web. While gravity pulls matter together, weaving galaxies into filaments and clusters, dark energy does the opposite. It's like an invisible hand pushing on the fabric of space itself, causing the vast voids between filaments to expand faster than the web's densest regions. This cosmic tug-of-war between gravity's pull and dark energy's push shapes how the web evolves not just today, but billions of years into the future. Picture the cosmic web as a rubber sheet slowly being stretched. Gravity holds the densest knots galaxy clusters tightly together, while the spaces between them grow wider as dark energy dominates. Over time, filaments become longer and thinner, like taffy pulled apart, while voids balloon into ever larger emptiness. This isn't just theoretical. Observations of distant supernova first revealed dark energy's existence in the 1990s by showing the universe's expansion wasn't slowing down, as gravity would predict it was accelerating. Now, surveys like DAISY and Euclid are mapping how this acceleration affects the web's structure by comparing galaxy positions across cosmic time. The consequences are profound. As dark energy stretches space, galaxies bound within filaments still move toward intersections, but the threads connecting them grow longer and more tenuous. Some simulations suggest that in tens of billions of years, galaxies outside our local supercluster will be pushed so far away by dark energy that they'll vanish beyond the cosmic horizon, their light stretched into undetectable infrared whispers. The web won't disappear, but it could become a patchwork of isolated islands, each clinging to their local filaments as the space between them becomes an unbridgeable gulf. Yet dark energy doesn't act alone. At smaller scales, gravity still dominates. Clusters like Virgo or Coma are so massive that their gravitational pull keeps nearby filaments intact, even as the voids around them expand. This creates a strange duality. While the largest structures drift apart, galaxies within filaments continue to collide and merge, birthing new stars in violent bursts of creation. It's as if the universe's fate depends on where you're standing. Within a filament, gravity's drama unfolds unabated, but zoom out and dark energy is rewriting the script. The wild card is how dark energy's strength might change over time. Some theories suggest it could grow stronger, eventually overpowering even the strongest galaxy clusters, a scenario called the Big Rip, where filaments are torn apart down to atoms. Others propose it might weaken, allowing gravity to regain control. Future telescopes like the Roman Space Telescope aim to measure dark energy's behavior with unprecedented precision by tracking how the web stretches across different epochs. Every new data point brings us closer to answering whether the cosmic web's grand design is destined to fade, or if dark energy's grip is just another phase in the universe's endless metamorphosis. What's clear is that dark energy isn't just a background force, it's an active sculptor. By stretching the voids, it indirectly shapes where galaxies can form. Regions too distant from filaments may never gather enough gas to ignite stars, as dark energy whisks potential material away too quickly. This cosmic bottleneck could mean that the golden age of galaxy formation is already behind us, with future galaxies doomed to starve in an ever-expanding desert. Yet even in this scenario, the web persists a testament to gravity's enduring grasp, holding fast against the dark tide. Understanding this balance isn't just about mapping the universe's past, it's about forecasting its ultimate destiny. Trying to comprehend the sheer scale of the cosmic web is like standing on a beach, staring at a single grain of sand while attempting to imagine every coastline on Earth. Even that analogy falls short. The filaments of this vast structure stretch over 500 million light-years in length, distances so enormous that if you traveled at light speed, the fastest possible, you'd need 500 million years just to cross a single thread. To put that in perspective, our entire Milky Way galaxy would be smaller than a freckle on this cosmic giant's arm. Think of Earth's largest geographic features, the Amazon rainforest, the Pacific Ocean, the Himalayas, and then multiply them by a factor beyond human intuition. The filament known as the Hercules Corona Borealis Great Wall, one of the web's most massive structures, spans roughly 10 billion light-years. That's nearly a seventh of the observable universe. If this wall were a mountain range, each peak would dwarf entire superclusters, with valleys so deep they could swallow thousands of galaxies whole, the truly staggering part. The cosmic web isn't just big, it's structured. Unlike Earth's chaotic mountain ranges or meandering rivers, the web follows precise patterns, with filaments intersecting at mathematically predictable angles. These junctions form nodes where galaxies cluster like bustling ports at the confluence of trade routes. The largest known node, the Shapley supercluster, contains tens of thousands of galaxies bound together in a gravitational maelstrom, all fed by the web's sprawling supply lines. But here's what makes the web's scale almost incomprehensible. It's still growing. As the universe expands, filaments stretch like cosmic taffy, pulling galaxies further apart even as gravity fights to hold them together. Some threads are elongating so fast that distant galaxies we see today will one day vanish beyond our observational horizon, their light stretched into oblivion. The web isn't static. It's a living, breathing entity reshaping itself on timescales that dwarf human history. Yet for all its immensity, the cosmic web isn't invincible. Dark energy, that mysterious force accelerating the universe's expansion, is slowly pulling the web apart at the largest scales. voids between filaments grow wider, stretching the web's threads thinner over billions of years. One day, far in the future, the web may resemble a tattered net, its connections severed by the relentless stretching of space itself. Even now, we're witnessing a snapshot of this epic struggle, gravity's patient weaving versus dark energy's inexorable pull. What's humbling is realizing that the Milky Way, for all its hundreds of billions of stars, occupies just one unremarkable strand in this vast tapestry. We're not at the center of anything. We're residents of a cosmic suburb, drifting along a filament toward the Virgo cluster like a leaf caught in a gentle current. The web's scale doesn't diminish us, though. It redefines what connected means. Every atom in our bodies was forged in stars that formed because the cosmic web channeled gas into galaxies, making us quite literally children of this invisible architecture. To stand beneath the night sky and trace the Milky Way with your finger is to touch just one thread in a tapestry woven across billions of light years, its patterns echoing the universe's very first moments. The web isn't just the largest structure, it's the universe's autobiography, written in galaxies and dark matter, waiting for us to learn how to read it. The cosmic microwave background and the cosmic web tell two chapters of the same cosmic story. One is the universe's first baby photo, the other its fully grown skeleton. The CMB, a faint glow of microwave radiation, captures the universe just 380,000 years after the Big Bang, when it cooled enough for atoms to form and light to travel freely. This afterglow shows us a newborn cosmos, smooth, uniform, with only tiny temperature fluctuations that would one day grow into galaxies and filaments. It's like looking at a black and white ultrasound of the universe before it took shape. Fast forward 13 billion years, and those subtle ripples in the CMB have transformed into the cosmic web, a sprawling, three-dimensional network of galaxies and dark matter. Where the CMB is a flat, two-dimensional snapshot, the web is the universe in full 3D, its filaments weaving through space like the branches of a colossal tree. The CMB's tiny density variations became the seeds for these structures, amplified by gravity over eons. Think of it like comparing a blurry sonogram to a high-resolution MRI. One shows potential, the other reveals the intricate reality. But there's a crucial difference in what these two snapshots reveal. The CMB is a relic of the universe's fiery infancy, a time when matter and energy were still coupled in a searing plasma. It freezes a single moment in time, unchanged since those first photons broke free. The cosmic web, on the other hand, is alive with motion, galaxies sliding along filaments, clusters merging, gas flowing into voids. The CMB is history preserved, the web is history in the making. Here's where it gets even more fascinating. The patterns in the CMB aren't just random, they match the web's modern structure with uncanny precision. Those slightly warmer spots in the ancient light, they became the dense nodes where galaxy clusters now thrive. The cooler regions, those evolved into today's vast cosmic voids. It's as if the universe left fingerprints in its baby picture, and we're just now learning to read them. Yet for all their connections, these two cosmic markers serve different purposes for astronomers. The CMB is our best window into the universe's first moments, revealing the exact proportions of dark matter, ordinary matter, and dark energy. The web, meanwhile, shows how those ingredients played out over time, like comparing a recipe to the finished meal. By studying both, scientists can trace how the universe grew from a near-perfect soup of particles into the structured tapestry we see today. The real magic happens when we combine these perspectives. When cosmologists run simulations starting from the CMB's initial conditions, they can predict the web's current structure, and the predictions match real observations astonishingly well. This isn't just confirmation of our models, it's proof that the universe's growth follows physical laws we can understand. The CMB gives us the starting point, the web shows us the outcome, and the physics in between is the story of everything. What's truly humbling is realizing these two snapshots are separated by almost the entire history of the cosmos. The CMB photons we detect today have been traveling for over 13 billion years, while the light from galaxies in the web might be much younger or older, depending on their distance. When we look at the CMB, we're seeing the universe before any stars or galaxies existed. When we map the web, we're seeing the result of all that came after: the birth of stars, the death of stars, and the slow, relentless work of gravity pulling matter into its grand design. This duality also reveals how much we've learned and how much remains unknown. The CMB's near-perfect uniformity still puzzles scientists. Why was the early universe so smooth? Meanwhile, the web's intricate filaments challenge us to understand how dark matter's ghostly grip could sculpt something so vast. Together, they bookend the universe's evolution, offering clues to mysteries like dark energy's acceleration and the ultimate fate of all structure. In the end, studying the CMB and the cosmic web isn't just about mapping the universe, it's about unraveling time itself. One shows us the dawn, the other the present, and the thread connecting them is the story of how simplicity gave way to complexity, how randomness became order, and how a universe of scattered particles became a web of galaxies with us against all odds here to trace its threads. Among the countless particles streaming through the universe, neutrinos stand out as cosmic ghosts so small, so elusive, they pass through entire planets like light through glass. Yet these nearly massless particles might hold surprising sway over the cosmic web's grand design. Born in the hearts of stars, supernova, and the Big Bang itself, neutrinos outnumber atoms in the universe by 1,000,000,000 to 1, and their sheer abundance means they could subtly shape how the web's filaments twist and stretch across the cosmos. Unlike dark matter, which clumps together under gravity's pull, neutrinos behave differently. They zip through space at nearly the speed of light, their tiny but non-zero mass giving them just enough gravitational influence to leave faint fingerprints on the universe's largest structures. Picture a river flowing through a canyon. Dark matter is the bedrock carving deep channels, while neutrinos are the breeze skimming the surface, barely noticeable. But over billions of years, even that gentle pressure can alter the landscape. Here's how it works. In the early universe, neutrinos were too energetic to settle into the growing dark matter filaments. Instead, they smeared out density fluctuations, acting like a cosmic iron smoothing over wrinkles in spacetime. This damping effect was subtle, perhaps thinning some filaments by a few percent or slightly shifting where galaxies clustered. Yet over billions of years, those tiny changes compounded, leaving the cosmic web subtly different than if neutrinos were massless. The evidence: supercomputer simulations that include neutrinos show filaments with slightly altered shapes, less dense in some regions, more stretched in others, compared to models where neutrinos are ignored. Observational hints come from galaxy surveys too. When astronomers measure how clustered galaxies are at different scales, the data fits better when neutrinos' smoothing effect is accounted for. It's as if the universe's blueprint has faint eraser marks where these particles gently blurred the dark matter's sharp lines. What makes neutrinos especially fascinating is how they bridge particle physics and cosmology. Their minuscule mass, so small scientists only confirmed it in the 21st century, comes from physics beyond the standard model, possibly tied to undiscovered particles or forces. By studying how neutrinos tweak the cosmic web, we're not just mapping structure, we're weighing the universe's lightest known particles on the grandest possible scale. Future telescopes like the Vera-C Rubin Observatory could spot these neutrino imprints by measuring distortions in the web's finest filaments, turning the cosmos itself into a colossal neutrino detector. Yet neutrinos aren't the only invisible players here. They're part of a larger cosmic tug-of-war between fast-moving particles called hot dark matter and slow-moving ones like traditional dark matter, cold dark matter. Too many neutrinos and the web's filaments would be overly smoothed, too few, and they'd be unnaturally jagged. Their presence is a delicate balancing act, one that suggests the universe's structure depends not just on dark matter's dominance, but on an intricate dance between fast and slow, hot and cold. The wildest implication, neutrinos might help explain why some galaxies exist where they shouldn't. Dwarf galaxies in the Milky Way's outskirts, for example, appear more scattered than cold dark matter models predict. Neutrinos' subtle gravitational nudges could be the missing piece, gently herding these small galaxies into slightly different orbits over eons. It's a reminder that even the universe's most ghostly particles leave trails if we know how to look. As we peer deeper into the cosmic web, neutrinos remind us that the universe's blueprint isn't just written in dark matter's bold strokes, but in the faintest whispers of particle physics. Their cosmic background acts with a surprising role, proof that even the smallest things can shape the largest structures given enough time. Black holes aren't just lurking in the darkness, they're active players in the cosmic web's grand drama, pulling strings from the shadows. At the hearts of nearly every galaxy cluster, supermassive black holes sit like cosmic puppeteers, their gravitational reach extending far beyond their event horizons. These behemoths, weighing millions or even billions of times the sun's mass, don't just consume nearby stars, they reshape the very filaments that feed them. Picture a spider sitting at the junction of its web, sensing vibrations along each thread. When gas from a filament drifts too close, the black hole's gravity yanks it inward, sparking violent outbursts of energy that can heat surrounding gas to millions of degrees or even blow it clear out of the galaxy. These feeding frenzies create bizarre cosmic feedback loops. As a black hole gorges on filament gas, it often spews out jets of plasma at nearly light speed, carving colossal bubbles in the surrounding intergalactic medium. The Chandra X-ray Observatory has captured these scenes in stunning detail, gigantic cavities in hot gas clusters, each marking where a black hole's outburst pushed back against the web itself. These eruptions can last millions of years, and their effects ripple through the cosmic web like shockwaves. Some filaments near active black holes get stretched and twisted, their gas heated too much to condense into new stars. In extreme cases, black hole winds can sever a filament entirely, cutting off a galaxy cluster's gas supply like a gardener pruning a vine. Yet black holes aren't just destroyers, they're also cosmic regulators. Their outbursts prevent too much gas from flooding into galaxy clusters, which might otherwise form stars so violently they'd burn through their fuel and die young. By heating and stirring the gas, black holes keep star formation on a slow, sustainable simmer. Simulations show clusters without active black holes end up crammed with dwarf galaxies, their filaments choked by unchecked star birth. It's a delicate balance. Too much black hole activity starves galaxies, too little lets them overeat. The most fascinating interactions happen where filaments collide with galaxy clusters. As gas streams along a filament toward a waiting black hole, it doesn't always fall straight in. Instead, it often spirals into an accretion disk, a glowing whirlpool of superheated plasma that can outshine entire galaxies. Some of this material gets funneled into the black hole's jets, while the rest is flung back into the web-like cosmic splatter. The Hubble Space Telescope has spotted galaxies where black hole winds blow filaments into eerie, glowing arcs, like smoke caught in a cosmic breeze. But black holes don't act alone. Their behavior is tied to the web's larger structure. When two filaments intersect near a cluster, they can funnel extra gas toward the central black hole, triggering more violent outbursts. This creates a feedback loop where the web feeds the black hole, and the black hole reshapes the web. In dense cluster cores, multiple black holes may even orbit each other, their combined gravity stirring the pot further. The upcoming Laser Interferometer Space Antenna LISA mission aims to detect the gravitational waves from these dances, offering new clues about how black holes sculpt their filamentary surroundings. The grandest black hole impacts might be written in the web's largest voids. Some theories suggest early supermassive black holes, born from the universe's first stars, could have heated surrounding gas so intensely they created dead zones where filaments struggled to form, seeding today's vast cosmic deserts. If true, these ancient monsters didn't just inhabit the cosmic web, they helped design it. Every time astronomers spot a black hole's jet piercing a filament or a galaxy cluster's gas mysteriously glowing, they're glimpsing one thread in an epic story of construction and destruction where the universe's hungriest objects shape the very skeleton that sustains them. The cosmic web's fate hangs in the balance of a cosmic tug of war, where dark energy's relentless push fights gravity's steadfast pull. For now, gravity holds the web's filaments together, guiding galaxies along their dark matter highways, but dark energy is slowly rewriting the rules. Imagine two opposing forces sculpting the universe, one building intricate connections, the other dissolving them into isolation. Over billions of years, this struggle will determine whether the web remains a vibrant network or frays into disconnected fragments. Some simulations paint a haunting picture. As dark energy accelerates the universe's expansion, the voids between filaments grow faster than the threads themselves. Galaxies bound within filaments still drift toward cluster nodes, but the spaces between these structures stretch so wide that distant threads may one day vanish beyond observation. It's like watching a spiderweb caught in a hurricane. The strongest strands hold firm, but the outermost threads snap, carried away by an invisible wind. In this scenario, the web never truly disappears, but it becomes a patchwork of isolated islands, each clinging to local filaments as the rest of the cosmos recedes into darkness. Yet not all scientists agree this fracture is inevitable. Alternative theories suggest gravity might maintain its grip far longer than we think. Galaxy clusters are so massive, some containing thousands of galaxies, that their collective gravity could resist dark energy's pull indefinitely. These dense knots would persist like mountain peaks rising above a flood, their filaments thinning but never fully breaking. Even as voids expand, galaxies within these fortified regions would continue colliding, merging, and birthing new stars, keeping the web's heart alive. The wild card lies in dark energy's nature. If its strength remains constant, the web's dissolution will be slow and incomplete. But if dark energy intensifies over time, a scenario called the Big Rip, even the mightiest filaments could tear apart atom by atom. In this extreme future, galaxy clusters would unravel, then galaxies themselves, then stars, planets, and finally the fabric of space-time. The cosmic web wouldn't just fade, it would shatter. There's a third possibility, though, one that hints at cosmic renewal. Some models suggest dark energy's influence could wane, allowing gravity to regain dominance. If that happens, filaments might thicken anew, pulling scattered galaxies back into a rejuvenated web. It's a cyclical vision of the universe where structure ebbs and flows like tides in a celestial ocean. What's certain is that the web's fate isn't just about distant galaxies, it's about us. The Milky Way's local filament still funnels gas into our galaxy, fueling star birth. But as dark energy stretches the web, even that lifeline could weaken. Future civilizations might gaze up to a sky where other filaments have faded from view, their light stretched beyond detectability. The universe could become a far lonelier place. Yet for now, the cosmic web endures a testament to gravity's patience and dark energy's slow-motion siege. Every map we make, every filament we trace, is a snapshot of this epic struggle. The web story isn't just written in the past or present. It's a narrative still unfolding, one where the final chapters remain as mysterious as dark energy itself. While dark matter remains the leading explanation for the cosmic web structure, a small but passionate group of scientists argues we've been missing something fundamental. What if dark matter doesn't exist at all? Enter modified Newtonian dynamics, or MUND, a radical theory suggesting our understanding of gravity itself is incomplete. Instead of invoking invisible particles, Mund proposes that gravity behaves differently at extremely low accelerations, like those found in the vast spaces between galaxies. Picture dropping a feather in a vacuum chamber. It falls just like a bowling ball because Earth's gravity is strong. But in the faint gravitational fields at galaxy edges, Mund suggests gravity gains an unexpected boost, mimicking the effects we currently attribute to dark matter. This idea isn't without merit. Mund accurately predicts the rotation speeds of many galaxies without requiring dark matter halos, a feat standard cosmology struggles with unless dark matter is carefully fine-tuned. Proponents point to oddities like ultra-diffuse galaxies, where stars move far faster than visible matter should allow, yet their motions align neatly with Mund predictions. Even some filamentary structures in the cosmic web appear statistically smoother than dark matter models anticipate, a possible smoking gun for modified gravity's influence. But Mund faces its own challenges. While it excels at galaxy-scale phenomena, it stumbles when explaining larger structures like galaxy clusters or the cosmic web's intricate filaments. Critics note that Mund requires additional tweaks like unseen, hot gas, or neutrinos to match cluster observations, edging uncomfortably close to reinventing dark matter under another name. Worse, the theory struggles to reconcile with the cosmic microwave background's precise patterns, which dark matter models nail effortlessly. The debate gets even thornier when quantum physics enters the picture. Dark matter fits neatly into theories like supersymmetry, which predict undiscovered particles, while Mund lacks a clear quantum foundation. Some researchers bridge the gap with hybrid theories like emergent gravity, where spacetime's microstructure creates gravity's apparent variation, or theories where dark matter interacts via unknown forces. Others explore wilder ideas like spacetime itself having memory, where past mass distributions subtly shape present-day gravity. What makes these alternatives compelling isn't just their potential to solve cosmic puzzles, it's their reminder that science thrives on dissent. Every anomaly in the cosmic web, every galaxy that rotates wrong, is an invitation to re-examine our assumptions. Whether Mund or dark matter prevails, the truth will likely be stranger than either, a reminder that the universe's grandest designs often hide their blueprints in plain sight. The cosmic web isn't just a scientific marvel, it's an artistic masterpiece, a celestial canvas where data and creativity collide to reveal the universe's hidden beauty. Scientists might map its filaments with equations and simulations, but it's often artists who bring those invisible threads to life, transforming raw numbers into visuals that stir the soul. Take the iconic Millennium Simulation, for example. When astrophysicists first generated its dark matter maps, the results were sprawling grids of particle densities fascinating to researchers but impenetrable to most. Enter data artists who color-coded those densities, stretched filaments into glowing tendrils, and rendered clusters as jewel-like nodes, turning abstract physics into a cosmic Van Gogh. These collaborations aren't just decorative, they're vital, helping researchers spot patterns their equations might miss while inviting the public to see the universe anew. One standout example is the work of artist Donna Cox and her team at the National Center for Supercomputing Applications. Using supercomputer data, they crafted 3D visualizations of the cosmic web so vivid they resemble neural networks or bioluminescent deep-sea creatures. The similarity isn't accidental. By deliberately echoing organic patterns, these artworks highlight a profound truth. The universe's largest structures mirror the branching veins of a leaf or the synapses of a brain. It's a reminder that the same physical laws shape galaxies and cells alike, a concept easier to grasp when you're staring at a swirling, luminous filament that could equally be a distant galaxy cluster or a close-up of dendritic growth. But art's role goes beyond metaphor. Some visualizations, like those from the Illustris TNG project, use sonification, translating cosmic data into sound. Dark matter densities become deep bass frequencies, while gas filaments shimmer as high-pitched tones. The result, a symphony of the cosmic web, where the universe's structure isn't just seen but heard. These multisensory approaches aren't gimmicks, they're research tools. Astronomers have used sonification to identify subtle asymmetries in filaments, proving that creativity can sharpen scientific insight. The public's encounter with these artworks often happens in planetariums, where full-dome projections wrap audiences in filaments of light. Shows like Dark Universe, produced by the American Museum of Natural History, use real galaxy surveys to project the web across curved screens, letting viewers float through its threads. The effect is humbling, a visceral sense of scale no textbook can match. Even abstract installations like Raphael Lozano Hemmer's Pulse Spiral, which maps participants' heartbeats onto a galaxy-like spiral, draw emotional connections between human experience and cosmic structure. What makes these collaborations revolutionary is their honesty. Artists don't just prettify data, they interrogate it, asking questions scientists might overlook. When painter Leah Halloran partnered with astrophysicists to depict dark matter's gravitational lensing, her cyanotype prints, made by exposing light-sensitive paper to celestial data, revealed distortions that sparked new discussions about filament density. Similarly, the Universe Awareness Project enlists children to draw galaxies, their uninhibited sketches sometimes mirroring real structures found in later deep field surveys. Art becomes a two-way street. Scientists inspire artists, and artists push science forward. The next frontier, virtual reality. Projects like Titans of Space let users don VR headsets to fly through the cosmic web, peeling back layers of dark matter like an archaeologist brushing dust from fossils. These immersive experiences don't just educate, they evoke awe, a feeling NASA studies confirm is key to sustaining public interest in science. And as AI tools like generative adversarial networks begin creating their own cosmic art trained on real datasets, we're nearing a future where the line between simulation and imagination blurs entirely. Ultimately, these artistic interpretations do more than illustrate, they bridge. A teenager gazing at a mural of the Hercules Corona Borealis Great Wall might not grasp redshift surveys, but they'll feel the web's grandeur. A physicist studying an abstract sculpture of void formations might suddenly see a new topological connection. In a universe where the most important structures are invisible, art doesn't just depict reality, it helps us perceive it. The cosmic web is too vast, too strange to be understood by equations alone. Sometimes you need a brushstroke, a melody, or a burst of light to reveal what math can only hint at. Imagine strapping on a VR headset and suddenly finding yourself adrift in the vast expanse of the cosmic web, dark matter filaments glowing around you like threads of neon light. This isn't science fiction, it's the cutting edge of astrophysics education. Tools like the Virtual Universe Project and the Titans of Space VR experience have transformed raw telescope data into immersive journeys, letting users navigate the web's filaments as effortlessly as scrolling through a city street on a map app. The effect is revelatory. What once existed only as equations on a blackboard or pixelated simulations on a screen now unfolds in 3 dimensions, with clusters like the Virgo supercluster looming in the distance like skyscrapers, while delicate tendrils of gas and dark matter stretch into the void like celestial bridges. These VR reconstructions aren't just artistic interpretations, they're built on real datasets from missions like the Sloan Digital Sky Survey. Developers feed millions of galaxy positions into game engines, then use gravitational algorithms to render the dark matter filaments connecting them. The result, a cosmic playground where you can reach out and touch a supercluster or watch galaxies stream along filaments like cars on a freeway. Some experiences even layer in sound design, translating cosmic microwave background fluctuations into haunting chimes or assigning deep bass tones to the densest nodes, creating a symphony of structure. For researchers, VR offers unexpected advantages. Traditional 2D maps can obscure the web's true geometry, but in virtual space, astronomers spot filament intersections and void boundaries with intuitive clarity. At MIT's Haystack Observatory, scientists use VR to walk through galaxy surveys, identifying subtle filament alignments missed in flat projections. One team discovered a previously overlooked tendril linking two minor clusters simply by noticing its curvature while navigating the simulation at an unorthodox angle. Proof that sometimes seeing in 3 dimensions reveals what math alone cannot. But the true power of these tools lies in their ability to democratize cosmic wonder. Planetariums from Tokyo to Chicago now host VR stations where visitors can pilot their own journeys through the web, zipping from the local group to the Hercules Corona Borealis Great Wall in minutes. Students in classrooms from Nairobi to Oslo manipulate the web scale, shrinking its billions of light years down to a room-sized model where filaments become arm's-length wires and voids are hollow spheres. The abstract becomes tangible. Dark matter isn't just a theory anymore when you feel the visceral awe of drifting through its architecture. Emerging technologies are pushing these experiences further. Haptic feedback suits let users feel gravitational tugs as they approach a filament, while eye tracking adapts simulations in real-time focus on a galaxy cluster, and the system highlights its connected threads. Some experimental platforms even incorporate treadmill floors, so walking forward physically propels you along a filament's path. These innovations aren't just gimmicks, they engage proprioception, the body's sense of movement, to cement spatial understanding in ways screens never could. Yet for all their sophistication, these tools underscore a profound truth. The cosmic web is so immense, so alien, that no visualization can fully capture its reality. Even in VR, filaments extend beyond the virtual horizon, their true scale slipping just beyond comprehension. That humbling gap between simulation and cosmos might be the most valuable lesson of all, a reminder that some wonders demand not just new technology, but new ways of seeing. As these virtual frontiers expand, they're doing more than teaching us about the universe. They're reshaping how we belong to it. The cosmic web isn't just a scientific revelation, it's a wellspring of inspiration for storytellers, game designers, and filmmakers who crave the grandeur of the universe's hidden architecture. Take Christopher Nolan's Interstellar, where the black hole gargantua isn't just a vortex of destruction, but a gateway threaded by invisible filaments of higher dimensional space. The film's portrayal of cosmic connectivity, where love and gravity transcend dimensions, echoes the web's real role as the universe's connective tissue. Nolan consulted physicist Kip Thorne to weave realism into the spectacle, grounding the film's trippy tesseract scene in actual gravitational physics. The result, a visceral sense that the cosmos isn't just empty space, but a dynamic network where every thread pulses with purpose. Video games have embraced the web's aesthetic even more boldly. In No Man's Sky, players walk between star systems along procedurally generated pathways that mirror the web's filamentary structure. Each jump a nod to how galaxies really migrate along dark matter highways. The indie masterpiece Outer Wilds takes it further, hiding its central mystery inside a quantum-entangled network of celestial threads, where ancient civilizations left clues about existence itself. These worlds resonate because they borrow the web's most haunting quality, scale. Staring at a galaxy map in Mass Effect with its glowing relay corridors feels eerily close to browsing a Sloan Digital Sky Survey visualization, proof that reality's design is stranger than any sci-fi writer's first draft. Literature has been dreaming of cosmic webs long before telescopes confirmed them. Olaf Stapledon's 1937 novel Star Maker envisioned the universe as a vast neural network, millennia ahead of dark matter's discovery. More recently, Lou Sixon's The Three-Body Problem trilogy imagined civilizations hiding in the web's voids to evade detection, a chilling twist on how real-world cosmologists use voids to test theories of dark energy. Even fantasy isn't immune. Brandon Sanderson's Cosmere universe literally runs on interconnected investiture threads, a fantastical metaphor for the filaments that power our own reality. What makes these depictions so compelling is how they tap into the web's duality, its blend of order and chaos. In Doctor Who, the Time Lord's regeneration energy crackles like filamentary lightning, echoing the web's real-life plasma currents. Marvel's Eternals reimagine the Celestials as cosmic weavers, planting seeds in planets like galaxies forming at filament nodes. These artistic liberties aren't just whimsy, they're attempts to humanize a structure so vast it defies intuition. By grafting the web onto mythic archetypes, the loom, the tree of life, the world's serpent artists give audiences footholds in an otherwise alien landscape. The web's influence spills beyond fiction into music and visual art. Electronic musician Jean Mitchell Jarre's Oxymore album used 3D soundscapes to simulate drifting through cosmic filaments, while Team Lab's digital installations morph visitors' shadows into glowing tendrils that branch like dark matter streams. Even fashion designer Iris Van Herpen's runway collections mimic filamentary patterns with dresses that seem spun from interstellar gas. This cross-pollination reveals a deeper truth. The cosmic web isn't just science. It's a cultural touchstone, a shared vocabulary for exploring humanity's place in the universe. Perhaps the most profound impact lies in how pop culture primes us for scientific discovery. When interstellar audiences first saw black hole visuals based on real equations, they weren't just entertained, they were conditioned to accept the universe's inherent weirdness. Now, as telescopes like Euclid map the actual web with increasing clarity, the public recognizes structures they've already glimpsed in games and films. Art doesn't just reflect cosmology, it prepares us for it, turning raw data into visceral experience. The next time you watch a hero navigate a galactic superhighway or hear a villain monologue about the fabric of space-time, remember, you're not just being told a story. You're being shown a mirror to reality itself. You don't need a PhD or a $1 million telescope to help unravel the mysteries of the cosmic web, just an internet connection and a curious mind. Projects like Galaxy Zoo have turned galaxy classification into a global collaboration where anyone can log on and help scientists map the universe's vast filamentary structure. Imagine sipping your morning coffee while flipping through celestial snapshots, tagging spiral arms or merging galaxies with a few clicks. What feels like a casual pastime is actually frontline research. The human brain's knack for pattern recognition often spots quirks algorithms miss, leading to discoveries like Hanny's Voorwerpen, a bizarre green cosmic cloud identified by a Dutch schoolteacher browsing Galaxy Zoo in 2008. The beauty of citizen science lies in its scale. Professional astronomers can't possibly scrutinize millions of galaxy images alone, but crowdsourcing unlocks that potential. Platforms like Zooniverse host dozens of cosmic projects, from tracing faint filaments in dark energy survey data to spotting cosmic voids in Hubble images. Each contribution stitches another patch into the cosmic web's evolving map. Some volunteers have even co-authored scientific papers, their names nestled alongside career astrophysicists' proof that exploration isn't reserved for those with telescopes. Here's how it transforms research. When thousands of eyes examine the same patch of sky, consensus emerges like cosmic wisdom of the crowd. A faint tendril between two clusters might escape one viewer but catch another's attention. And when multiple volunteers flag it, scientists know where to aim their spectrographs. This method has exposed unexpected galaxy alignments along filaments and peculiar star-forming regions where web threads knot together. The data isn't just academic, it trains machine learning algorithms to better simulate the web's growth in supercomputer models. Beyond galaxies, projects like radio galaxies zoo enlist help tracing the invisible highways of ionized gas that weave through filaments, while Backyard Worlds, Planet 9 lets users hunt for rogue planets drifting in the web's dark interstices. There's even a role for creatives. Platforms like SETI Live invite volunteers to interpret unusual signals that just might, hint at cosmic structures beyond our current models. The most inspiring part, these projects dissolve barriers. A retiree in Tokyo, a student in Nairobi, and a bartender in Buenos Aires can all contribute to the same cosmological breakthrough. Every classification, every tagged anomaly is a stitch in humanity's collective quilt of cosmic understanding. So the next time you gaze at the night sky, remember, you're not just a spectator. With a few clicks, you can become a cartographer of the universe's grand design, tracing threads in the dark that bind us all. The cosmic web doesn't just redefine the universe's structure, it rewires our very sense of place within it. For centuries, humanity clung to the idea of cosmic centrality, first placing Earth at the heart of creation, then our sun, then our galaxy. Each revelation chipped away at our exceptionalism, but the web delivers the final blow. We aren't just peripheral, we're participants in an intricate network where even the grandest structures are threads in a larger tapestry. Our Milky Way isn't a lonely island. It's a single stitch in a fabric woven across billions of light years, tethered to galaxies we'll never see by filaments we've only just begun to map. This realization carries a quiet, humbling, a cosmic perspective shift rivaled only by Copernicus's revelation that the Earth orbits the Sun. Yet this humbling isn't a demotion, it's an invitation. The web's vast interconnectedness suggests that existence isn't just about isolated points of light, but about relationships. Like neurons in a brain or roots in a forest, galaxies gain meaning through their connections. Even the atoms in our bodies, forged in stars that formed because filaments funneled gas into galactic nurseries, carry echoes of this cosmic kinship. The calcium in our bones, the iron in our blood, all once flowed along these invisible highways. We aren't just observers of the web, we're its offspring, breathing stardust spun from its architecture. Philosophers have long grappled with humanity's smallness against the cosmos, but the web reframes that smallness as belonging. Ancient Stoics spoke of sympatheia, the interconnectedness of all things, while indigenous cosmologies envisioned celestial rivers linking Earth to the stars. Modern physics now offers a startlingly literal version of these intuitions. The web's filaments aren't metaphors, they're gravitational realities demonstrating that isolation is an illusion. When a supernova explodes in a distant filament, its shockwaves ripple through gas that may one day form new planets. Every cosmic event whispers across the web, a reminder that causality stretches far beyond our local bubble. This perspective also reshapes existential questions about life's rarity. If the web funnels ingredients for life, water, carbon, energy along preferential channels, then habitable worlds might cluster like berries on a vine, thriving where filaments intersect. Suddenly, Fermi's paradox, where is everyone, takes on new dimensions. Perhaps life isn't randomly scattered, but concentrated along the web's fertile branches, waiting for us to decode the map. Or perhaps we're early arrivals in a universe still weaving its threads with vaster connections yet to form. The web's most profound gift might be the way it marries awe with agency. Unlike the crushing indifference of a purely chaotic cosmos or the rigid determinism of a clockwork universe, the web suggests a middle path, a universe structured enough to foster complexity, but dynamic enough to surprise. It challenges us to see ourselves not as passive stardust, but as active interpreters of a story still being written. Every telescope pointed at a filament, every simulation of dark matter's dance is part of that story, a reminder that curiosity, too, is a kind of cosmic thread, binding us to the universe's unfolding mystery. The most thrilling chapter of the cosmic web story hasn't been written yet. It's unfolding right now in labs and supercomputers around the world, where scientists are probing frontiers that could rewrite our understanding of reality itself. At the cutting edge of this quest lies a tantalizing puzzle. What happens where the web's vast filaments intersect with the bizarre rules of quantum gravity? Picture this: dark matter's tendrils stretching across billions of light years, but at their absolute smallest scales, perhaps fraying into loops or vibrating strings so tiny, they dance to the tune of entirely unknown physics. Teams at CERN and the Perimeter Institute are racing to model these extreme environments, where the web's cosmic architecture might merge with the fuzzy uncertainty of the quantum realm. One radical theory suggests the web's filaments could be threaded with cosmic strings, hypothetical defects in space-time left over from the universe's birth. These ultra-dense, infinitely thin strands, predicted by some quantum gravity models, might weave through dark matter like wires through clay, subtly warping galaxies' motions in ways current telescopes are just beginning to detect. The Laser Interferometer Gravitational Wave Observatory (LIGO) scans the cosmos for ripples that could betray these strings' presence, while quantum simulators recreate their potential effects using ultra-cold atoms in labs. It's detective work on a galactic scale, where every anomalous galaxy rotation or unexpected gravitational lensing distortion could be a clue. Meanwhile, the hunt for dark matter is entering its most creative phase. Traditional searches focus on WIMP, weakly interacting massive particles, but newer experiments like the Action Dark Matter Explorer are chasing after Action's ghostly particles that might form swirling currents along filaments, bending light in telltale ways. There's even wilder speculation. Could dark matter be primordial black holes, forged in the Big Bang's first seconds and now lurking in filaments like pearls on a string? The James Webb Space Telescope's keen infrared eyes are scanning the web's oldest regions for signs of these invisible giants distorting starlight. Perhaps the most mind-bending frontier is the quest to unify quantum mechanics with relativity through the cosmic web structure. Theories like loop quantum gravity propose that space-time isn't smooth and continuous as Einstein imagined, but pixelated, a network of intersecting loops that might manifest as faint granularity in the web's largest filaments. If true, this cosmic pixelation could leave imprints in how galaxies cluster at the web's nodes, a signature the upcoming Euclid Space Telescope might spot. Other researchers are exploring whether the web's structure holds keys to dark energy's nature. Could voids between filaments be expanding faster because quantum fields there fluctuate differently? It's like the universe handed us a riddle wrapped in filaments, and every new observation peels back another layer. What makes this era so electrifying is how technology is catching up to theory. Quantum computers, like those at Google and IBM, now simulate how dark matter's quantum properties might shape filaments, tasks impossible for classical supercomputers. AI trained on millions of simulated universes spots anomalies in real galaxy surveys that human eyes would miss, hinting at physics beyond our current models. And in underground labs from South Dakota to Italy, ultra-sensitive detectors wait for the faintest flash or vibration that might betray dark matter's true identity. The next decade promises revelations that could overturn everything. When the Square Kilometer Array radio telescope comes online, its millions of antennas will map hydrogen gas flowing through filaments with unprecedented detail, potentially revealing hidden forces at work. NASA's Nancy Grace Roman Space Telescope will peer back to the web's infancy, catching the moment when quantum fluctuations first stretched into cosmic threads. Each experiment is a torch illuminating a different corner of the labyrinth, and we're just beginning to glimpse how the passages connect. This isn't just academic curiosity. Unraveling the web's quantum underpinnings could unlock technologies straight from science fiction. Imagine harnessing dark matter's gravitational tendrils for navigation, or tapping into quantum spacetime itself for communication. More profoundly, it forces us to confront whether the universe's structure is inevitable or a frozen accident of quantum probabilities. The cosmic web isn't just something we're mapping. It's a mirror reflecting our deepest questions about existence, waiting for its next layer of secrets to be pulled from the dark. The cosmic web stretches beyond human comprehension, a delicate yet unbreakable lattice of dark matter, galaxies, and gas that spans billions of light years, binding the universe together in a silent, intricate dance. It's humbling to realize that every star, every planet, every speck of dust in the night sky is cradled within this vast cosmic architecture, suspended like dewdrops on an invisible spider's silk. From the faintest filaments weaving through the voids to the densest galaxy clusters glowing at the intersections, this web is the universe's grand design. An echo of quantum ripples from the Big Bang itself, stretched across time and space into the structures we see today. Yet for all we've uncovered, the web remains shrouded in mystery. Dark matter's true nature eludes us. The full reach of filaments fades into the unobserved depths of the cosmos. Even our most advanced simulations are still just sketches of a reality far more complex. And that's the beauty of it. The cosmic web isn't just a scientific frontier, it's an invitation to wonder. Every new discovery peels back another layer, revealing just how much we have yet to learn. So the next time you step outside and gaze at the stars, remember this: you're not just looking at distant points of light. You're seeing the glow of galaxies strung along threads of an unseen tapestry, one that connects everything, including you. The iron in your blood, the calcium in your bones, every atom in your body was forged in stars that formed because this web funneled gas into cosmic cradles. You are quite literally stardust woven into the universe's fabric. The adventure doesn't end here. With telescopes like Euclid and the Vera C. Rubin Observatory coming online, we're on the verge of mapping the web in greater detail than ever before. Who knows what secrets we'll uncover next? If you're as captivated as we are, don't miss out. Hit subscribe and join us as we continue exploring the cosmos' greatest marvels. The universe is vast, mysterious, and breathtakingly connected, and so are you. Look up your part